Welcome to Math260, Lesson 6, Introduction to Matrices. Up to now we've worked with numbers and vectors, and we'll see in this lesson that matrices are kind of an extension of the idea of vectors. In fact, we'll look at matrices in a way as collections, as a collection of vectors. So here's the definition. A matrix is a rectangular array of entries. Usually the entries are numbers, but they can be very general mathematical entities. But for our purposes in this class, the entries will either be numbers or an algebraic expression representing a number or a possible set of numbers. We say that the matrix A has dimensions m by n when it has m rows and n columns. And everything in matrices goes row, column, RC, when we use a pair of numbers to refer to a matrix. So here's a couple of examples. The matrix A has algebraic expressions as entries. It has 2 rows and 3 columns. The entries in the first row are x in the first position, 2 plus x in the second position, and 3y minus 4 in the third position. As we can see, so we would say this is a 2 by 3 matrix because it has 2 rows and 3 columns. Similarly, B is a 4 by 5 matrix. In this case, all the entries are numeric, and we can see that that's true because it has 4 rows and 5 columns. We can refer to individual entries in a matrix by what we call indexing, and the notation is if A is an m by n matrix, m rows and n columns, then A sub ij, or we sometimes just say Aij, is the entry in the ith row and the jth column, where of course these indices have to be within bounds. The row index is between 1 and m, the number of rows, and the column index is between 1 and n, the number of columns. So here's an example of indexing a matrix with 4 rows and 3 columns, so A would be 4 by 3. A11, sometimes written without the comma, sometimes just as it looks like A11, would be 14 because A11 is the entry in the first row, first column. A32 is 17 because 3-2 picks out the third row, second column. So here's third row, second column, 17. A23, notice the indices are ordered because A32 is different than A23. So A23 would be the element in the second row, third column. Second row, third column is a 5. And finally, A24 would be invalid because that would ask for the entry in the second row, fourth column, but A only has 3 columns. It will often be useful to think of an m by n matrix as a collection of n vectors, where each column of the matrix is one of the vectors. And of course, since the matrix has m rows, each of those vectors would be of length m. So here's an example where A is a 3 by 4 matrix. We can think of it as a collection of 4 column vectors, where the first column is the vector 3, 6, 9, the second column is the vector minus 9, 5, 3, the third column is 11, 19, minus 6, etc. So thinking about it in this notation, a vector in Rm can be expressed or thought of as an m by 1 matrix. That's what we've been doing when we've written column vectors. So we could also consider this vector to be a 3 by 1 vector, 3 rows, 1 column. As we'll see also, we'll have reason to sometimes view the rows of the matrix as vectors instead of the columns. This will be particularly true when we get to matrix multiplication. So, matrix addition. If A and B are 2 matrices of the same dimension, they must have exactly the same dimensions in order to add them. Then we define the sum of the 2 matrices by adding corresponding elements. Notationally, if C is the matrix that results from adding the matrices A and B, where they're both m by n, they both have the same dimensions, then the ijth element of the resulting matrix is the sum of aij and bij. That is simply the sum of the corresponding elements, the elements in the same position in the two matrices, that we're adding. So here's two matrices, A and B. To add them, they have the same dimension. We first have to check that. They're both 3 by 4 matrices. So we add corresponding elements. The first entry in the result is 2 plus 6. In the first row, the second entry in the result is 3 plus 9. In the third entry in the first row of the result is 8 plus 17, etc. And you can see we've simply added the corresponding elements, and we do the arithmetic. 2 plus 6 is 8, 13 plus 9 is 22. Notice the result is a matrix of the same dimension. C, this resulting C matrix, is also a matrix with 3 rows and 4 columns, exactly the same as the two matrices we added. Notice also that this definition is compatible with vector addition. If we think of these matrices as a collection of vectors, what we've done is add the corresponding vectors. We've added the first column of A to the first column of B to give the first column of C as a vector. And similarly, we've added the second column of A to the second column of B, giving the second column of the result, using the rules for vector addition. We can also multiply a matrix by a scalar just as we multiplied vectors by scalars. So if A is an m by n matrix, we define the multiplication of A by the scalar or real number k as in the following way. If C is the matrix that results, when we multiply the matrix A by the scalar k, then all we do is multiply each entry of A. So the ijth entry of C is k times the ijth entry of A, just like we did for vectors. So here's a couple of examples. The matrix A given here, then 3 times the matrix A, we simply multiply each entry in A by 3. So the first entry is 3 times minus 8, minus 24. The second entry in the first row, 3 times 11, 33. 3 times 13, 39. 3 times 3, 9, etc. So all we're doing is multiplying each entry in A by the scalar. Given two matrices here with algebraic entries in them, these are both 2 by 2 matrices, then if we compute the linear combination 2A plus B, we first multiply the matrix A by 2. That would give us 4x, 6x, 8x, and minus 10x, and then add the matrix B using addition term by term. That would give us 4x plus 4y as the first entry in the answer. Then 6x, remember we doubled, we're doing 2a, so it's 6x minus 2y, and then the others follow, 8x plus 3y and minus 10x plus y. So that wasn't too hard, was it? It's adding matrices element by element and scaling matrices by multiplying each element by the scalar is pretty straightforward, and the combination of those lets us do linear combinations. So here's some matrices for practice. So you're asked to pick out a couple of elements in the matrices A and B, compute 2A, A plus B, 3A plus 2B, and please pause the video now, work these exercises, preferably by hand, and then when you've got them done, continue the video. Okay, hopefully you did that. You paused the video and worked these out for yourself. Let's look at the solutions. So the first element asked for was A23. That's the element in row 2, column 3 of the matrix A. Row 2, column 3 is a 12, so A23 is a 12. The next entry asked for was B31. That's the element in row 3, column 1 of the matrix B, so that's 14. A plus B, we simply add element by element, so it's 8 plus 2 is 10, 17 plus 15 is 32, 1 plus 6 is 7, 2 plus 17 is 19, 6 minus 7 is minus 1, 12 plus 10 is 22, etc. And then for the last expression, the linear combination of matrices 3a plus 2b, it's good to do this in a couple of steps. So we first multiply the matrix A by 3, multiplying each entry by 3. 3 eighths are 24. 3 times 17 is 51. 3 times 1 is 3. 3 times 2 is 6, etc. And then we multiply the matrix B by 2, doubling each entry. 2 times 2 is 4. 2 times 15 is 30. 2 times 6 is 12, etc. And hopefully then you added these two matrices element by element, giving 24 plus 4 is 28. 51 plus 30 is 81. 3 plus 12 is 15. And again, we were combining 3 by 3 matrices, so the answer is a 3 by 3 matrix. Okay, so for homework, download and study the notes for Lesson 6, Introduction to Matrices. This material, by the way, is covered in Section 2.1 of our textbook. And then we'll get practice with matrix arithmetic, have a quiz on our vector material, focusing on the last two lessons, vector arithmetic properties and vector projection. And then on the plate for our next video is number 7, matrix arithmetic properties. That ends this lesson.